A butterfly's wing flap in Brazil would be enough to cause a hurricane in Indonesia. Edward Norton Lorenz, 1893. Kyoto, Japan. Young lawyer Henry Stimson and his wife Mabel White are honeymooning in Kyoto. The newlyweds are enchanted by the colorful Oriental city and its ancient history. They will remember this visit for the rest of their lives. May 11, 1945, Los Alamos, USA. A special U.S. Army commission draws up a list of priority targets for atomic bombings. Kyoto tops the list, being Japan's largest industrial center. Underscoring the city's cultural significance, Secretary of Defense Henry Stimson personally removed it from the list. This made Hiroshima the U.S. military's primary target. The next city at risk of bombing was Kokura. August 9, 1945, Japan. The crew of a U.S. Air Force B-29 bomber receives a particularly important order from their commanders. The Kokura military arsenal must be razed to the ground. For the mission, a state-of-the-art bomb, more powerful than any previously used, is loaded aboard the plane. However, the city is shrouded in such thick fog that the crew can't make out the target. The plane's captain, Charles Sweeney, decides to continue the flight to Nagasaki. Thus, sentimental memories from 50 years earlier and a normal meteorological event influence the fate of millions of people. And this story is just one of many examples where seemingly small events can give rise to enormous, incredibly far-reaching consequences. This phenomenon is commonly referred to as the butterfly effect. But in reality, it's just one part of a vast field of science known as chaos theory. To better understand the correlation between small arthropods and destructive weather events, let's go back to the recent past. In 1961, mathematician and meteorologist Edward Lorenz attempted to predict the behavior of atmospheric flows using computer models. He believed that thanks to new computing capabilities, he would be able to forecast the weather with unprecedented accuracy. However, the results of the calculations puzzled the scientist. To try to speed up the calculation process, Lorenz divided it into phases so that the final results of the previous phase served as the starting conditions for the next. Some of the resulting values were slightly rounded by the computer. This was so negligible that it shouldn't have had any significant impact on the final result, or so the scientist thought. However, in reality, it turned out that the results of the continuous and gradual calculations differed significantly. Subsequent studies revealed that the system of equations Lorenz was attempting to solve was inadequate for modeling atmospheric processes. However, as often happens in science, a poorly formulated problem proved to be a step toward a surprising and unexpected discovery. In his search for answers, the mathematician discovered that all possible solutions to the system clustered around two conventional positions he called attractors. If each solution were represented by a point in a 3D coordinate system, it would ultimately form a shape reminiscent of a butterfly's wings. Interestingly, even the slightest change in any initial parameter can dramatically shift the final calculation result from one wing to the other. Indeed, Lorenz wasn't the first to discover such an effect. Similar ideas were expressed by the German philosopher Johann Fichte and the French mathematician Henri Poincaré in their works. However, it was Lorenz who transformed the vexing error of mathematical modeling into an elaborate theory capable of providing answers to many questions. Needless to say, hundreds of scientists would contribute to the notion of chaos in the decades that followed, and the theory itself has come a long way. Its mechanisms can be applied to describe complex phenomena and processes such as turbulent flows, the evolution of biological species, social interactions, and stock market prices. The laws of chaos define the motion of celestial objects and stellar explosions, the rise of empires and the disappearance of continents. And to get to the heart of these factors and regularities, the notion of chaos must first be defined from a scientific perspective. First, it should be noted that any chaotic structure is subject to fairly rigid and clear physical laws, but they are so complex that the system's behavior appears unpredictable. For this reason, structures of this type are also known as deterministic chaos, referring to the fact that their behavior is predefined. This is the main characteristic that distinguishes them from stochastic systems, which are based on truly random events. If the behavior of a chaotic system is supervised multiple times with absolutely identical initial conditions, it will react the same way. However, for a structure based on pure chance, the result will never be the same. For example, experiments showed that the decay of unstable nuclei in a sample of radioactive material occurs entirely by chance. We can calculate the approximate number of atoms that transform in a given time interval, but with the current state of technological development, it is impossible to predict the precise moment at which a given nucleus should decay. The exact mathematical definition of chaos is as follows. A system must exhibit nonlinear characteristics, be globally stable, but at the same time have at least one oscillating equilibrium point. At the same time, the fractal dimension of the system must be at least 1.5. This convoluted statement is quite difficult to decipher, unless you're a professional mathematician, of course, rather than a layman. Simply put, it can be expressed in three main points. First, the system must be nonlinear. Imagine influencing a structure in one way or another and getting predictable feedback. It's logical to assume that after several such interactions, the resulting change will be equal to the sum of all the individual interactions. However, this isn't the case for a nonlinear system, and as a result, the structure will change more or less than expected. This was the effect Lorentz observed in his calculations, which encouraged him to continue his studies. Second, a chaotic dynamical system must be sensitive to initial conditions. That is, it must exhibit this butterfly effect. This means that however small and almost negligible a change in the initial conditions may be, it can force the system to develop in a completely different way. Third, as a system develops, its individual parts should overlap and interact with each other. Such interactions are usually overlooked in classical physics. However, they often prove to be a serious omission. It's the monitoring of a multifaceted influence that makes chaos theory models so elaborate and so similar to real structures. Think back to 13.8 billion years ago. Only a few quanta of time would have passed since the hypothetical Big Bang. There is no matter or energy as we know it around us, and the four fundamental interactions are interconnected by a single bizarre force. The physical laws we know are not yet applicable at this point. However, other laws are in place, equally rigid and predetermined for the future development of the system. At the same time, a minimal change anywhere in the developing universe can completely alter its future, whatever the reason. It seems our reality was literally born out of chaos, in the scientific sense of the word. Now imagine what it will be like about 1 million years later. The space of that time would have become more like the one we know, although there are no stars or planets around. There are only countless clouds of primary hydrogen floating around the young universe. The hydrogen is exposed to the pressure of gravity. This forms gravitational centers that will soon become the first stars. These gas clumps are rather irregularly distributed, without any reference frame. They are also massive enough to exert a gravitational influence on each other. At the same time, moving any of the protostars or slightly altering their mass will affect not only their evolution but also that of their immediate surroundings. This means that the laws of chaos continue to govern the universe. Over the next billions of years, the primary stars burned out and exploded, saturating the universe with heavy elements. New stars were born from clumps of hydrogen, with nearby clouds of cosmic dust swirling in gigantic vortices and forming protoplanetary disks. It's easy to observe the familiar patterns of chaotic motion and interaction in their structure. And so 4.5 billion years ago, the solar system was born. This story could go on forever. Supernovae, the formation of celestial bodies, atmospheric phenomena, and ocean currents. Everywhere we look, there are examples of deterministic chaos all around us. Its laws determine how children will grow, how the economy will develop, and how society will change. The entire universe is permeated by myriad connections, and each of us is part of this system. And it feels as if a tiny butterfly in a remote corner of the planet has just flapped its wings. If you want new videos, subscribe to the channel and get a subscription. It doesn't take much for you, but it's essential for us to keep publishing content like this.